The James Webb Space Telescope, JWST, is fundamentally altering our understanding of the universe, compelling scientists to reconsider long-held assumptions about the cosmos, and even prompting discussions about rewriting textbooks. Among its most unexpected triumphs has been the imaging of Pluto. When Webb turned its highly sensitive instruments toward the distant dwarf planet, few could have predicted the revolutionary insights that would follow. The images that came back were not merely clearer. They were transformative, providing an unprecedented look at one of the solar system's most mysterious worlds. For decades, Pluto has been an enigmatic body on the fringes of our solar system, cloaked in icy darkness and largely beyond the reach of detailed study. Even after NASA's New Horizons mission in 2015 offered a groundbreaking flyby of Pluto, numerous questions remained. With the deployment of Webb's advanced infrared sensors and high-resolution capabilities, scientists are now able to observe Pluto with clarity never before possible, and the implications of this new data are profound. Pluto, once considered the ninth planet before being reclassified as a dwarf planet in 2006, continues to captivate the scientific community and the public alike. Orbiting over 3.6 billion miles from Earth in the Kuiper Belt, Pluto's immense distance and small size have historically made it a challenge to study. Even the renowned Hubble Space Telescope could only provide faint, blurry images. However, Webb's 6.5-meter gold-coated mirror and its location beyond Earth's atmosphere have revolutionized our ability to observe faraway celestial objects. When Webb focused on Pluto, it captured intricate textures, surface features, and atmospheric elements that had never been seen before. Unlike traditional telescopes that operate primarily in the visible light spectrum, Webb observes the universe in infrared wavelengths. This means it can detect subtle heat signatures and compositional variations invisible to optical telescopes. In the case of Pluto, this allows scientists to peer through its thin atmosphere, study temperature variations, and detect surface changes that hint at ongoing geological processes. The newly released infrared images of Pluto are filled with intricate details. They reveal the planet's nitrogen ice plains, mountainous regions, and even possible signs of seasonal shifts in the atmosphere. One of the most remarkable findings is the newfound clarity of Sputnik Planitia, the iconic heart-shaped region on Pluto's surface. While first observed by New Horizons, Webb's infrared sensors have uncovered variations in brightness and texture across this plane, suggesting dynamic processes such as sublimation or deposition of surface ices. These indicators imply that Pluto may still be geologically active, which is surprising given its small size and the frigid temperatures it endures. Furthermore, the data collected by Webb allows scientists to study Pluto's thin, nitrogen-dominated atmosphere with greater precision. Composed of nitrogen, methane, and carbon monoxide, Pluto's atmosphere is extremely tenuous and cold. Yet in the infrared, subtle shifts in temperature and composition become easier to detect. These observations are now helping researchers track changes in atmospheric pressure and temperature over time, offering valuable insights into Pluto's seasonal cycles during its 248-year orbit around the Sun. Webb's capabilities extend beyond Pluto itself. The telescope has also captured detailed data about Pluto's 5 known moons, particularly Charon, the largest and closest. Charon is especially intriguing because of its size, about half that of Pluto, and its synchronous orbit, meaning the same side always faces Pluto. Webb's imaging has revealed previously unseen details of Charon's surface, including evidence of frozen ammonia and complex hydrocarbons. These discoveries point to the possibility of a more active geological history than previously thought. The telescope has also observed Pluto's smaller moons, Styx, Nix, Kerberos, and Hydra, which have historically been difficult to study due to their small size and great distance. With Webb sensitivity, scientists can now refine the orbits of these moons, analyze their surface compositions, and better understand their formation and evolutionary history. These findings contribute to a richer understanding of the Pluto system and of the broader dynamics at work in the outer reaches of our solar system. Perhaps most intriguing is how this new data revives the debate about Pluto's planetary status. When the International Astronomical Union reclassified Pluto as a dwarf planet, it was in part due to assumptions about its size, orbit, and relatively simple geology. However, Webb's observations reveal a complex world with active geology, a layered atmosphere, and even hints of subsurface oceans, characteristics typically associated with full-fledged planets. Some astronomers are now questioning whether Pluto's demotion was premature. Beyond the issue of nomenclature, the real value lies in what these new observations teach us about planetary formation and evolution, particularly in the cold, distant reaches of our solar system. Webb's success with Pluto also underscores the telescope's broader utility in exploring the Kuiper Belt, a region teeming with icy bodies left over from the formation of the solar system. Pluto is just one of thousands of such objects. With Webb's advanced capabilities, astronomers can now turn their attention to other dwarf planets like Eris, Makemake, and Haumea, along with still undiscovered objects hidden in the Kuiper Belt shadows. Each new observation adds another piece to the puzzle of how our solar system formed and evolved over billions of years. While the Hubble Space Telescope revolutionized our view of the cosmos through visible and ultraviolet light, Webb's infrared sensors allow it to see what Hubble cannot: faint heat emissions from cold, distant objects. This ability is especially useful for studying Pluto and similar icy worlds, which reflect little visible light, but radiate in the infrared spectrum. Capturing such a detailed image of Pluto required an extraordinary level of precision and technological coordination. Webb's fine guidance sensors had to account for both the telescope's motion and Pluto's slow drift against the background of stars. The fact that Webb was able to track an image such a small, distant, and fast-moving target speaks volumes about the engineering excellence behind the telescope. This flexibility allows Webb to shift seamlessly from observing galaxies billions of light-years away to focusing on dynamic objects within our own solar system. Such versatility opens up exciting possibilities for future studies, including more in-depth examinations of moons like Neptune's Triton or other Kuiper Belt objects that remain enigmatic. As scientists continue to analyze Webb's data, new questions emerge. Could there be a hidden subsurface ocean beneath Pluto's icy crust, similar to those suspected on moons like Europa or Enceladus? What mechanisms power the apparent geological activity on such a cold and distant world? Are there cryovolcanoes releasing volatile materials from Pluto's interior? While Webb alone cannot answer all these questions, it helps to define them more clearly and provides a critical observational data needed to guide future missions and theoretical models. The telescope's contributions to comparative planetology are especially significant. By comparing Pluto's nitrogen cycle, surface chemistry, and atmospheric behavior with those of other icy bodies, such as Titan or Triton, scientists can better understand the broader processes that shape planetary evolution across the solar system and even in exoplanetary systems. Beyond the scientific breakthroughs, Webb's image of Pluto holds deep symbolic meaning. Not long ago, Pluto appeared as a blurry dot barely distinguishable even with our best telescopes. Now we can see its frozen plains, jagged mountains, and delicate atmospheric layers in stunning detail. We can trace the contours of its iconic heart-shaped plane and observe the orbital dance of its moons. This leap in our observational capability represents not only progress in planetary science, but also a triumph of human ingenuity, curiosity, and persistence. Every image and data point is a culmination of decades of work by scientists, engineers, and visionaries who dare to imagine what might be possible. Webb's image of Pluto is more than just a scientific milestone. It is a new chapter in humanity's ongoing journey to understand the cosmos. From its discovery in 1930 to the New Horizons flyby, and now to Webb's high-resolution imaging, Pluto's story is one of relentless exploration and discovery. The telescope is not just capturing light from distant corners of the universe. It is illuminating the path forward, revealing new questions and inspiring new missions. As long as we continue to reach outward with the right tools and the determination to explore, the universe will continue to reward us with awe-inspiring revelation.